with where we were at. If A divides B, as we did A, so let's try it on the other B. So remember how these work. You just got to make up numbers to put into the A, B slots and see if it's true or false. So they're saying if A divides B, so let's put it over here. If A divides B plus C, then A divides B or A divides C. This is great. This is great, you know, because it makes you think about logic and how it works, if-then statements, and, or, all that. All right, so give that one a try. Give that one a try. Try to make up an A and a B and a C. So make them easy. Don't do hard. Don't do like 79. Hard numbers. 2, 3, 4, 5. Numbers like that. Right? And now, remember what we talked about last time with the if. Remember, didn't I talk about a dog? Or, yeah, if it's a dog, then it's black. Right? Which is not true. But the way how would you prove me not true when I make that if-then statement? If it's a dog, then it's black. That's not true. How would you prove me wrong? Find a dog that's not black. And you go, look at that brown dog. Or that white dog, so you're wrong. If it's a dog, then it's black is not good logic. So to prove somebody's if-then statement wrong, right? Let me write that out. It would help. If it's a dog, then it's black. I'm wrong when I say that. And the way you would prove me wrong, is you would have to meet my if. You can't find a cat that's white and say, aha, see, look at that cat, Mr. Heron. That wouldn't prove me wrong. I didn't say anything about cats. I said if it's a dog, it's black, right? So you gotta meet my if. Whenever somebody makes an if-then statement logically to prove them wrong, you gotta meet their if. You gotta find a dog. They talked about dogs, right? So I'm talking about an A that divides. So you gotta meet the if. So what you should try to do, what I'm saying, you should try to do on these if-then things, is you should try to find an A, B, and C that meet the if. And then see if it happens to meet the then or not. So pick an A, a B, and a C, where A does divide into B plus C. You know what I mean? Somebody got one. What's an A that goes into B plus C? What do you got? 2 goes into 3 plus 1. That's a great example, actually. 2 goes into 3 plus 1. 2 goes into 4, right? 2 goes evenly into 4. So that's an A, B, and C that meet the if. That's a dog. Now we can see if the then follows. Then, they're saying, the A, right? A is 2, B is 3, C is 1, right? The A will go into the B. Is that true? Does 2 go evenly into 3? No, not evenly. It's got a remainder, huh? Or, okay, if not that, then A will go into the C. What's C1? Does 2 go into 1? No. We found a dog. We met their if. And it wasn't black. So what's their statement? True or false? False. That's not true. That's not true. If A goes into B plus C, then it goes into one of them, either B or C. It does not. Here's a case where it goes into those numbers added, but it doesn't go into either number individually. That's a false statement, isn't it? That's faulty logic. See that? See how we determine that? All right. How about C? I'll try C. Oh, yeah, let me explain what the not thing. Everybody good with B? Questions on B? I know you guys have 100 questions, but I don't have time to answer them all. I'm just kidding. Sorry, are we good? All right, let's try. Let me give a fresh screen then. Look there at C. So on C, if A, now I put a not with a line, that means not. That means, and some of the ways you'll see it written also is like that. They'll slash it out. In math, whenever you have a symbol slashed out, it means not. I just wrote the word not, but you could see it either way. So they're saying A does not divide into B. So if A does not go evenly into B, and A does not go evenly into C, it doesn't go into A and C, then A will also not go into B plus C. So notice, if it doesn't go into B or C, then it doesn't go into them either. That's what they're saying. So see if that's the case or not. Now remember, you've got to meet the if. Right, everybody with me on the logic? You've got to meet the if. You got to meet the if. So both parts of the if. It's an and, right? If I said, if it's a dog and it's got fur, then it's black. You'd have to find a dog that's got fur. Or if it's a dog and it's, I don't know. Can't even think of another example. If it's a dog and it's not a poodle, whatever. You have to meet the whole if. Meet the whole if there. So make up some numbers. And then see if the then follows or not. Okay, so somebody got one? What's an A that doesn't go into B? You want it to not go in. So somebody give me an A and a B where A doesn't go into B. 2 and 3? Yeah, 2 does not go evenly into 3, huh? That's good, okay. And now this A's got to be the same. Once you've chosen A, it's still the same over here. And what's another number we need to see now that A also doesn't go into? 5, great. So 2 doesn't go into 3, 2 doesn't go into 5. We met their if. They said, you got a number, 2 doesn't go into 3 or 5. Then 2 will also not go into them added, 3 plus 5. 2 also does not go into 8. Is that true? No. It does go into 8. Is that not thing confusing? It's not true. It's true, in other words. Right? They're saying 2 doesn't go into 8. They are wrong. 2 does go into 8 evenly. Right? They said, then it will not go in. Well, it did go in. They are wrong. Is that good? Okay with all that not stuff? How about D? Try D. If A divides B and B divides C and A divides C. Try that. You know, these aren't just silly little number examples. These really help you to think logically about if, then, logical statements, things people say, things lawyers say, and legal documents say, and, you know, people say they're writing complex articles and technical journals. It's all about the logic of the if, then, and how these things flow. So this really is actually very beneficial, this kind of thinking. It's not just silly little number things. It's making us think real carefully, precisely about logical statements. Which is why you came to college, right? Because you wanted to come out. No, I know. Mainly you want to get a job, and then that's good. That's a good desire. But along the way, it'd also be nice to grow in your knowledge of things. I'm sure you'd enjoy that. So this will do that for you. It really will. They say one of the best things, if you want to, that studying math makes you better at reading comprehension. That's, official academic people say that all the time, and it's true, because math makes you read really precise, really careful to improve. Doing these kind of things will improve your ability to read complex technical writing. So, if A goes into B, and B goes into C, then A goes into C. So we got to meet the if, right? That's logical. If somebody makes a statement, we got to meet their if. So, somebody got an A that goes into B? 2 goes into 4. Beautiful. 2 goes into 4. That's certainly true. There's my A and my B. Now the B, I got to use the same thing here, so I got to use 4 again, right? Because we already said B is 4. So what's something else I could use for C then? 8, right? That's beautiful. So that meets the if, right? If 2 goes into 4 and 4 goes into 8, certainly does. Then, now the A, got to use it. What was the A? The 2 will go into, what was C? 8. Then 2 will go into 8. Yeah, it does. Now, that doesn't mean it always does. Could be the case that I just happen to pick lucky numbers. Do you realize that doesn't really prove it? You know what I mean? That's just because one, that'd be like me saying, hey, if it's a dog, then it's black. And then I pointed to a picture of a dog on the internet and it was black. And I went, see, I'm right. All dogs are black. Well, one black dog doesn't prove that all dogs are black. Just like one situation with numbers that works doesn't mean this is always true, Well, then how do you decide if it's always true? Maybe try another set of numbers. I mean, at some point, the only way to actually know is to do a math proof, and we don't want to do that. That's like hard. So instead, we'll just hope for the best. I know it sounds kind of lame, but we'll pick a couple of number situations and hope it's true. So if you're not convinced, we're thinking the answer is true at this point. At least it was true for our example. You could try some more numbers if you want. Somebody got another set of numbers they picked out? If it was my test, I'd probably try one more set. Anybody do a different set of numbers? Something that goes into something?
3 goes into 9.
3 goes into 9. And 9, because you got to reuse the same thing, the B and the B. 9 goes into 18. Good one. Then, the A will go into the, right, if the first number goes in the middle, and the middle goes in the last, then the first will go in the last. 3 will go into 18. Does it? Yeah, perfectly. 6 times, huh? So it's true again. So, we've seen 2 dogs, they're both black, all dogs are black. I mean, again, that's not 100%, but yeah, this is true. Can you feel a little bit logically why it's going to really always be true? If the first number goes into the middle, but if A goes into B, that means A is inside of B, huh? It's in there. Like if we broke down the primes, A is really inside of the primes of B. And B, his little pieces are inside of C. So if A's in B and B's in C, of course A is going to be in C, huh? Make sense? That is true. All right. We good? Here, and it says D does not divide into A squared. If D does not divide into A squared, then D will not divide into A. Yeah. All right, try that out. So you got to meet their if, right? To address an if-then statement, you got to meet their if. So meet their if there. If D does not divide into A squared. Okay, so can you give me an example where D does not divide into A squared? Anybody?
If D is 3 and A is 2.
So 3 does not go into, does not go into 2 squared. 3 doesn't go into 4 evenly. It's a good one. So that's the case. If that's the case, then 3 will not go into just the plain number, not squared. That's true. 3 doesn't go into 2. That's true. So it worked this time. Does that mean it always going to work? I think it's true. If you don't go into A squared, then you don't go into A times A, then you cannot go into A. Yeah, that's got to be true. Yeah, so if D, do you kind of feel it? If a number does not go into A squared, so if D does not go into A times A, that's what A squared is, right? A twice. So imagine if A is like 6, 2 times 3, 2 times 3, and D doesn't go in there. So D has something that doesn't go in, like a 7 in him. He might have a 2 as well. So I'm thinking primes. See, I always think primes when I go to thinking about this. Right? 2 times 7, 14, will not go into whatever, 6 times 6, 36, because of that 7. So if one number doesn't go, then there's no way that number is going to go, the 2 times 7 is going to go into just a single 2 and 3. Yeah, that's true. That's a true statement. So I don't know if I'm being any help. Is that making sense? Is that good? One of these is tricky. It doesn't. They all kind of look very similar, A, B, and C, don't they? D does not go into A squared. Oh, I just did C. Yeah, that was C. Okay, no wonder it looks the same. It is the same. And then A, if it goes into A squared, if it does not go into A. Oh, yeah, how about B? Yeah, let's do B. B is the tricky one. Let's try B. B. Let's do B. Let's go backwards and do B. I didn't notice this was a tricky one. If D does not go into A, then D will not go in to A squared. Try that one. D does not. This is. I'm just giving you a warning. This is a hard one. This is number 6, I think, isn't it? I believe. Let's try that one. Anybody coming up with anything? D does not go into A. Somebody got some numbers? How about if I go, well, 3 does not go into 2. Certainly. There's my D. There's my A. And so if D, then 3 will not go into 2 squared, meaning 4. That's true. So it's always true. Well, it's true that time. It is true that time. There is a time when it's not true. This one's more tricky. This one's often true, but not always true. It's like saying all dogs have 4 legs. If it's a dog, then it's got 4 legs. That's almost always true. But we know that's not really. There are some 3-legged dogs, right? And so this is like that. This is a more tricky one that has a subtle situation in which it's actually false. Anybody see it? Kim?
So since it's like there's like the potential of it being false, and we get this kind of question on an exam, and we test it out and it comes out true, and it comes out true, would we just circle true or would we circle false?
Yeah, I mean that's where. Yeah, yeah. My answer is you need to. So this is a harder one. I'm not going to give you a lot of these, but my answer is you would plug in one set of numbers, second that looks true both times, and then your sense of numbers needs to. I mean, it's a hard one. I'm pushing you here. You got to. Yeah, the answer is going to be false actually, and it's going to take some careful thinking about numbers. You got an idea?
And 4 does not go into 2, but 4 goes into 2 squared.
Well said. You see, 4 doesn't go into 2. And so 4 doesn't go into 2 squared. Oh, no, 4 does go into 2 squared. Good job. See, there is a case that clearly breaks it, right? So that's false. That's not true. Even though it's often true, it's not always true. They're saying it's always true. When you say it is then, that's what you're saying. If it's a dog, then it's got 4 legs. I'm saying all dogs have 4 legs. So that was an A. That was B. Wasn't that B?
Yeah.
Whoops. That was B. That was B there. Yeah, so B's a more tricky one. B's actually false. Good counterexample there. See, that's a counterexample. That's a dog that doesn't have 3 legs. That's rare. But that is a counterexample, right? But they said if you don't go into a number, then you're not going to go into that number squared. Well, that's not the case. 4 doesn't go into 2, but it does go into 2 squared. So they're not right. It's not a true statement.